device used, the timing device used to detonate it. Again, look in the cracks there. They're very often found there. Very important to look there. They can also be found in objects blown far away because they started off near the detonation site, but the detonation blew them away. So you got to be careful with it. You got to be careful and got to know where to look and know how to look for all these things. Also, we have to examine the soil and debris at the explosion crater because, again, this is where the unreacted explosives might be, and also the byproduct, the end products of it. And because what we're trying to do is we're trying to find out what was the explosive. What was it? Was it TATP? Was it dynamite? Was it C4? And if we know what it is, we might be able to find the source of it. You know, like who sold it? Who sold them the stuff? Or where are they making these explosives in maybe a homemade lab, some home lab and home. So it's very, very important to find the detonating device. This is actually easy to recognize because you usually don't find these things where the detonation takes place. You find some complicated, half blasted or mostly blasted, box full of wiring. That's you pretty much found your detonating device. And these things have clues. Again, well, where was the material? Where were the components of this detonating device? Where did they come from? You might even be able to find some DNA evidence on them. It's possible. So we want to find the detonating device. It's recognizable where it is. I mean, it's near the crater, near the source of the explosion. It could be blown away far away, but again, it's relatively easy to recognize it. Now, it's still possible. It has evidence, so we don't want to avoid contamination of it, even though it might have been blasted like anything. Still, if anything remains, any evidence remains, we want to avoid contaminating it. So the standard precautions will apply just in case. We used gloves, disposable gloves, so as not to get our DNA on it if we were looking for DNA evidence. Cover our clothing, so again, our DNA or what we are doing does not contaminate the evidence. The evidence, when found, has to be placed in metal airtight containers like paint cans. This is similar to what was seen in the case of fire evidence, where we take the debris or the ash, we put it in airtight paint cans. And for a very similar reason. The explosive might be a liquid and it can evaporate. We want to keep as much of it as possible. So we put it in airtight paint cans. It should be metal, not plastic, because we're talking about explosives and pipe bombs, and you find often sharp metal pieces, especially if the thing blasted a lot of metal. The metal doesn't warp and blast out in nice smooth sides. It blasts out in sharp edges. So it'll cut through plastic containers. Use metal to contain this evidence. And believe it or not, if you find some explosive, some residue, it might actually leak through plastic evidence bags. We put this in airtight metal containers. Now, for low explosive, like gunpowder or smokeless powder or the double base powder, the things we mentioned before, the black powder, that stuff. These are powders, and if we wipe the surface of the evidence area, we can pick up these dark powders, and they can be analyzed in the microscope. And these powders, they have a distinct shape, so we can get photomicrographs. We take a picture of it and compare it to the ones in the University of Central Florida. They have a database of different kinds of low explosives, so we can identify it. You can identify it with that. But also by their chemical and physical characteristics. They have a database. Once we have this black powder that we suspect, we will analyze it and compare it to the database that they have there. High explosive residue is a little bit harder to identify. It's not in the form of a black powder, and often it's only found in microscopic amounts. Use less of it than the black powder, so less of it is found. It's hard to find, but again, you can certainly use the spectroscopy and other ways of identifying it. What is very often used for explosives, specifically for explosives, is the portable ion mobility spectrometer. You can even carry it in your hand. It's like about a third of the size of a suitcase. Anyway, it's an ion mobility spectrometer. what it does is first it vacuums up residue, or you can just take a Teflon fiberglass disc to wipe things down. So you get that. You get the source. You put it in there. And what it does, and you put it in, well, the sample area of this ion mobility spectrometer. What it does, once you get the sample, it will hit it with an electron beam, another beta source like 63 nickel that produces beta radiation, basically electrons. So we use the electrons to ionize the chemicals of this sample. And different chemicals get ionized differently. They will move through the electric field at different speeds, and you can separate them and thereby analyze them. So a little bit more about that. First, what's done is we heat it up, and it becomes a gas. Now, this gas is hit with this radioactive nickel, the 63 nickel, or any beta source that will hit it with a lot of electrons. This will ionize the gaseous molecules. Okay, then we put them, again, they're ionized, we put them in an electric field. The ions with greater mobility, the ones they move faster. They're all ions, but some of them will move faster. Some chemicals will move faster. Some of these the residue of the explosives will move through at different rates, and we can separate them. Not only will we separate them, but we'll know what they are by which speeds they move. So we can identify the fuel used in the explosive, or the oxidizing agent from the explosive. This is a form of chromatography where different things move through a medium at different speeds, and the retention profile, where how far each one might have gotten or how fast they went, is compared shows what the different components are and what the different chemicals are. So we can again put our let's say our sample in this beam. It goes through it. Some will go through faster than others. Some will get farther than others. You get the idea. It's just like chromatography, and we compare this to known explosives, and we can see if the retention profile of this sample was the same as that of C4. Then we know that the explosive was C4. This is again initial testing. It does require confirmatory. It's like a presumptive test. It tells us pretty much what we know, but what we need to know, what it is, but we need to confirm it. And there are other ways of doing that. We take the debris, we wash with acetone and water. Now there are organic parts and that don't mix with water, and there are inorganic parts that dissolve in water easily, like the ammonium nitrate we mentioned is very easily soluble in water. This sodium chlorate that also dissolves very well in water. So the water, when we wash it, it will dissolve in the water. We can pick it up by washing it with water. The other things are dissolved in the acetone. The organic parts are dissolved in the acetone. A lot of the fuels, the ANFO, the ammonium nitrate fuel oil. The fuel oil will not dissolve in water, but it will dissolve in the acetone. So we wash it with acetone and water. So now that we have our samples dissolved in acetone and water, we analyze the solution that contains the fuels, the acetone, and the explosives, and the oxidizing agents. What we do is we put it in a thin layer chromatography. That'll tell us how many components there are. We mentioned that before in the lecture on chromatography. And very important, we put it through a GCMS, gas chromatography, mass spectroscopy. We make it turn into a gas. We send it through a column, and the different components will be separated by how well they stick to the column. And it goes through a mass spectrometer. Once we separate it, it goes through a mass spectrometer where the compound is